So this is real-time monitoring of metal transfer and melt pool for gas metal arc directed energy deposition, which we all know it's a additive manufacturing process. In particular, wire-fed directed energy deposition processes are basically the standard welding assisted additive manufacturing, and in particular gas metal arc assisted uh, directed energy deposition is typically nothing other than using the same gas metal arc process but in a much more controlled manner, controlled wire feed, controlled arcing, and controlled deposition. Everything is in a very controlled manner so that the deposition can be made as finely as possible with very little disturbances and with minimum spatter and so on. So there is one aspect, of course, that we have to use one of the very good power sources. Our topic is not that right now, but assuming that we have a sufficiently advanced intelligent gas metal arc power source that can provide deposition or as well as arc wire feed rate in a fairly controlled manner, the requirement here is much more stringent compared to simple welding processes or simple gas metal arc welding process. Among all the additive manufacturing processes, this is having a sheer advantage that it can provide a very high deposition rate simply because it uses a feedstock, wire as a feedstock. And so fabrication of medium to large scale parts can be made at a very competitive cost. So these two are, very important aspects why there are a lot of new investments and research is being carried out in this direction. And as we all know, this is nothing other than same coming from the group of wirearcadditivemanufacturing manufacturing, but I think we should talk more of GMA DED because it's a much more easy to understand and not yet some kind of patented or so. It's a much more basic term. So current challenges in this process are primarily dimensional inconsistency as we go on depositing layer by layer, porosity and surface roughness, increasing heat accumulation as the deposition moves from base to upper layers, lower to upper layers. And of course, then similar to welding, those problems are also there that we have designed a path and how to ensure that the movement of the wire or the torch would follow the exactly planned path. And if there is a possibility to ensure that in case there is a mistake, the movement can be self-corrected. All these challenges can of course be, as I said in the beginning, can be on one side handled by designing or developing newer power sources, more advanced kind of stuff. But on another side, development of real-time monitoring and control systems, which are quite successful in several welding processes, including very fast welding process like laser beam welding. Application of such real-time monitoring methods are yet not very popular, and I would say they have just begun. So the primary objective of this work was to develop a robust real-time monitoring methodology. The hope is that perhaps it can be moved advanced a step further to develop some kind of closed loop control feedback system so that the process can be even self-corrected to get a better quality part. So what is the stuff that we are trying to talk about? If we see a typical power source, okay, which will be, and the wire would be fed by a robot which will take care of the path planning and deposition strategy and so on. But more importantly, if we look at this particular picture, this gives us an idea, a bird's view of what really we are trying to talk about when we say modeling or monitoring of the process as such. So typically, if we consider that this is the direction the deposition is happening in a particular layer, along a particular layer, we are trying to talk of a couple of thermal cameras first that would look at the surface of the melt pool and try to capture the thermal images which can be converted to temperature field with certain accuracy, which would be used further to see or to analyze the typical melt pool dimensions. On another side, perpendicular to the deposition, we can also think of putting some kind of high-speed camera that can look at the longitudinal view of the melt pool as well as the deposition events, the sequential events of the deposition. Because we have learned that the typical low heat input process that is very much used for gas metal or directed energy deposition, it requires some specific type of metal transfer. Many of us might be already knowing short circuiting transfer or short arc based metal transfer, which is fairly difficult to control, but there are power sources which can to some extent provide a robust deposition in that range. But it is still required to be controlled or monitored to visualize whether the metal transfer is happening uninterrupted or there are some interruption or something else is happening. So the idea is, and everything has to be sort of moving with the wire feeder, because this is the key to success. The wire feeder contains the filler wire. So as the deposition will move on, arc will move on, so everything has to be moving on with it also and see how things are happening. So this is a typical setup that is kind of built in this lab, and experiments have been conducted. And let us see how things are kind of done in different ways. So we have taken experiments in the unidirection as well as in bidirectional scanning, because it is already known that bidirectional scanning often provides a better dimensional accuracy compared to unidirectional. But these are all kind of repeated trial and error experiments. So this kind of monitoring of temperature field would also allow to see how things are evolving. That's another plus point of doing real-time monitoring of the whole process in a transient manner. So typical wire feed rate, printing travel speed, which, as you know, in welding we used to talk of the welding speed. So this is nothing other than the same thing, but here we just have different terminologies so that we are not misled. So the idea of using different combinations of these wire feed rate and travel speed is nothing other than to see whether there is how to understand the effect of heat input, how to understand, wire feed rate, how to understand the effect of travel speed, and so on. So the first thing what we have tried is the monitoring of current and voltage, the transient one, because if we are able to do that, we can estimate the actual arc power, heat input per unit length. And secondly, along with that, if we can also do a visualization of the metal transfer, then we can exactly correlate at different points through the current and voltage cycles the metal transfer is happening, because these current and voltage cycles in this type of process is very, very important. They have kind of specific type of pattern they are made in, so that they can current and voltage transients can contribute to the transfer of metal in a systematic regular manner. So typically when we see through the video camera, what you just seen from here, this video camera from longitudinal section, we would see something like this. This is a single shot. We'll see the length of the pool in a longitudinal section. We'll see also the filler wire and how the droplets are coming. So you understand, when you want to look at the droplets coming from this, we must be looking at a very high frequency. So normal thermal camera cannot handle that. So a high-speed video camera is required, because we need to look at a very higher sample speed. On the other hand, when you look at only the melt pool surface, we are looking on the top view of the melt pool. So we can look at a sort of region of interest like this, where this would be the region that the camera will see, and camera should be able to designate the melt pool region and adjoining solidified region. Of course, what you see here is that there would be certain obstructions because we have the wire feeder, and this has to kind of handle all the cameras. So there would be little blockage. If you look at, we have to look at from the back. So when it is moving, because the cameras are placed slightly at an angle behind it, there would be slight blockage very near to the arc center, which we cannot see, and we have to do certain back calculations to figure out how much is that. And once we do that, there are different thermal cameras also that we have used. There are two color thermal camera and also monocolor thermal camera. The key difference, I do not want to go into a lot of details of that, but the key difference is that the monocolor thermal camera basically depends on a single emissivity factor to convert the spectral radiation into temperature field. This is of course a little erroneous because emissivity depends on temperature. So when we use a single emissivity value to convert radiation over a large field, it provides certain error. Whereas the two color camera, basically they consider two typical spectral wavelength and corresponding spectral radiations, and a ratio of that is providing the temperature field. In a way, we do not have to provide a single conversion factor for converting the radiation to the actual recorded radiation from the surface to the actual temperature value. But remember, when you want to do that, it is very important that we have to have in the camera, in front of the camera, suitable filters so that the radiations that are coming should be well within this range of wavelength of lambda 1 and lambda 2. All right. So we need to design all these so that we don't get erroneous results. But when we do that, let us now look at the results. For example, what we get. The typical high-speed data recorder can give us this kind of records like current and voltage transients, what you can see, and at different instants. These are typical important instants, through a current cycle, what we see here. So it starts from here and it moves up to here. As you can see, the current moves up from a very low value to a very high value for melting to start at the feeder wire. Then the current drops down to reduce the heat input so that the deposition of the molten metal from the filler wire can be possible at a low arc power. That would reduce, almost minimize the spatter at the time of detachment of the molten metal from the filler wire. This is one of the unique technology. Okay, and nowadays there are several power sources which provide it in some ways or the other. Now, the target to see here is that whether this is exactly happening as it is designed. What you can see also here, if we increase the wire feed rate from here to here, almost 3 meter per minute to 6 meter per minute in GMAW process, we all know this is connected to the automatic adjustment of the current and voltage transient. So the current also increases. So with this, we have tried to see what would be the effect of different heat input rate on the final melt pool temperature as well as metal transfer rates. But more importantly, this is to note that this is possible to be recorded by using a high-speed data recorder in a very fast responsive manner, and this analysis can also be possible in a very fast manner by using today's computer infrastructure, computational setups. If we try to look at dynamic metal transfer, when we look at through the high-speed camera, we see all those 1, 2, 3, 4, 5 what we have just seen. So the arc starts, you look at an intense current pulse, you remember that there was a very high current, then the current is reducing. We can see that the arc is actually reducing in size, although the drop has not yet been detached. Then the short circuiting phase starts, which is the unique type of metal transfer here, and then there is a small pinch. That means a small current is there. If you remember, there was a sudden increase in current here. This is to pinch the drop from the filler wire to the melt pool. So this strategy must work all throughout. This strategy must work all throughout, and this is what you can see when you look at through the high-speed camera. And the camera can easily detect that in case there is a sudden disruption of the metal transfer, or it is going in a very regular manner like this. And when we look at these different instances, it can be designed through the camera, and it can actually show how at different rate of heat input, different type of metal transfer events occur. These are all three regular processes. I did not want, at this very moment, I don't have a situation where there is a lot of disruption, but you can see in a case where these parameters or these process conditions are not set properly, there will be a lot of spatter, which will of course increase the process instability and also dimensional inconsistency of the final bed. So this is the contribution of the video camera over the real-time monitoring. Not only this metal transfer, we are also seeing throughout this longitudinal section of the melt pool. Don't forget that, because this is giving us an idea of what is the length of the pool. That's one of the most important thing, because this decides also the rate of cooling, for example. You see it further, very interesting, when we look at two different type of scanning, it clearly shows that in unidirectional scanning, the pool is always, the melt pool is always inclined to the horizontal section for some reason. But in case of bidirectional scanning, we see always a very stable pool. Almost like linear over the layer as it is progressing. So this is very interesting, and one of the sort of analysis that we could figure out is perhaps that in case of unidirectional scanning, because we are always coming back to the original point, the starting point where we have finished the previous layer, perhaps this creates a more heat accumulation at the starting point rather than a distribution of heat through the layer. And this might be creating this kind of, a sort of flowing of the molten metal always at the starting point, right? And here, in contrast, in the bidirectional scanning, there is a more uniform distribution of heat through the layer length, which perhaps is the reason for getting a melt pool length which is much more uniform. We are still looking into this more and more results. And next comes to the thermal cameras. When you look at the thermal cameras, we see splendid situations that we would not have been able to see in any other way. We can actually see the evolution of the pool as it moves. As you can see here, so three different conditions, for example, and at layer 1, layer 5 and layer 10. What you see here, for example, if we go from layer 1 to layer 5 to layer 10, as we are moving to upper layers, the melt pool is kind of increasing, the length size of the melt pool. That is not only important, what is also visible here, we see the melt pools are getting more and more asymmetric, right? And this is what we also observe, that as we go to upper layer, especially with high rate of deposition, a lot of molten metal, it gets kind of flowing on both sides or in one side if the process is not controlled properly, and we get a very wavy bead surface as we move on. So this is kind of intuitive, but most importantly, what is shown here, that this can be kind of detected and also measured very fast, whether it is unidirectional or bidirectional. Most importantly, we can also see that the range of error that we see when we look at through the two-color camera and the monocolor camera, there are not much error also, because we are principally focusing on the melt pool area. So monocolor camera, which is a much cheaper alternative compared to a two-color camera, is also a good alternative for this kind of real-time monitoring for surface temperature field, because If we look at here, for example, layer 2, this is for unidirectional with a 2-color camera, which is supposed to be more accurate. And if we compare this with this, there is not much difference, roughly 10% difference of the melt pool length. Width is more or less the same. So this is some advantage of also visualizing that maybe a monocolor camera sometimes can be also used, because this provides a relatively cheaper alternative. More importantly, what we also see that all those that we have been studying in different ways can also be explained from this real-time recorded surface temperature field. That means, for example, if we increase the arc power or wire feed rate, we see an immediate increase of melt pool width and length. If we increase the printing travel speed, so that would reduce the rate of heat input for unit length, so it immediately brings a narrower and more elongated temperature field. These are all available here, we can see it directly. As we go up to the higher layers, we see an increase of melt pool area. This is also very intuitive because it is actually increasing the heat accumulation, so rate of heat loss through the already deposited layers is continuously reducing. Effect of scanning strategy, we have noted that it's always smaller melt pool length for bidirectional scanning because of a more uniform heat distribution through the layers compared to unidirectional scanning, which always gives a much more asymmetric kind of pool length through the layer. And now comes, once we record this, if we have a fast analysis, fast responsive system to analyze these temperature records, we see that we can get a huge amount of information that are of real importance to us. For example, we can see the temperature contours through the length of the layers along different layers. Like what you can see here, this is the typical temperature contour along the center line of the melt pool. Okay, as we see for different layers, as we go up, we see the length of the pool is actually more and more increasing. Okay, we can do that simply by doing an arithmetic of seeing when the temperature contour, instantaneous temperature contour along the layer is basically intersecting with the liquidus temperature line. So that tells us what would be the length of the pool on a particular layer. And this also shows that there is a difference between unidirectional scanning and bidirectional scanning. The point to be noted here that all these can be easily done, easily built in a system which can do this in no time once the temperature record is available and they are fairly robust and reliable. Not only that, one very important information, as you all know, that in additive manufacturing in particular, not only in powder-based process, also in filler wire-based process, the layer-wise variation in cooling rate is a big problem. You know, that also varies or yields different mechanical properties through the layers. So once the temperature field is available from the camera, again, a simple sliding frame analysis can be done internally just by doing a simple computational logic, just to see, use a frame and how it is moving on an observation point, and looking at the temperature and time of that observation point very quickly in a fast responsive manner, we can actually also calculate the thermal cycle very fast. Once again, of course, we have not done that yet. This is all done in a post-processing manner, but this can be done. These are not very difficult in a monitoring terminology, I believe. So this shows us again most of the facts that are not yet unknown, that are not really unknown to us. For example, if we see S1, S2, S3, three different processes. S2, for example, it has the maximum rate of heat input, so its cooling rate is slower, for example. So higher rate of heat input yields slower cooling rate. This is known and it is clearly showing, and these are all obtained from the recorded temperature field by the thermal cameras. So the thermal cycles, once we get, that is temperature time, again we can put this to boundary like liquidus temperature, solidus temperature, and see how much time goes through this time to solidify, Very simple thing, and we can actually calculate the cooling rate at solidification, and we get that idea. And if we can do it, the idea is if we can do it much fast, perhaps we would be able to also do certain decision based on this. That means if the cooling rate is really varying much, there can be ways to control the process so that the variation can be minimized, because it is known that this will affect the microstructure property, cracks, and so on. And here again, if we see that the analysis showed that the results that we are producing, we are getting, are very much intuitive in nature. This is the reality. Okay. For example, if the rate of heat input is much higher, the cooling rate is slowing down. Okay. Not only that, the cooling rate is very high at the initial layers because the heat is dissipated through the substrate very fast. But as you are going towards the upper layer, because the solidified build already is getting more and more elevated temperature, so the rate of heat loss is slowing down, dampening. So the cooling rate is slowing down. So these are values which are direct, raw, real-time monitored, measured values. And if we can develop a fast responsive system that can utilize these and do control the process, perhaps the variability in the process can be reduced much more. One last thing that we would like to show further is the melt pool dimension. This is one of the challenge in especially wire arc additive manufacturing in general, or gas metal arc directed energy deposition in particular, that the variability of dimensional inconsistency. Again, if we can see that the image from the high-speed camera can immediately provide us the average depth and length. Likewise, the thermal image from the thermal camera provide the width, because they are in two different sections. Okay, and this can again show us the different melt pool dimensions. Okay. And again, the observation is that this is reliable. There is no difference in what is actually happening, what we know by intuition should happen. The record also shows exactly the same thing. Like, for example, the length increases as the travel speed increases. The depth reduces as the travel speed increases, for example. So all these informations are obtained. We have also looked at the final builds and did some characterization of these builds at different height and found out how much the results that we are extracting for the computed temperature field are in variance with the actual measured width of the build cross section at different height. So this is also done, and we have seen roughly these are the kind of variation. That's what we have noted in different cases with a large number of trial and error. So in unidirectional, lastly, in unidirectional, I have told you that we have noted that the difficulty in unidirectional scanning, these are the typical builds that are obtained in unidirectional and bidirectional scanning. And as you can clearly see, when it is unidirectional, that means the wire is always coming back at this point, starting point, and going to this direction. It's always something like this. We always get a field which is inclined in like this, whereas in a bidirectional scanning we get a much better profile with a much uniform also the width through the weld height. And the reason is, of course, intuitive. It's not very difficult because the heat accumulation is kind of asymmetric here compared to in the bidirectional scanning, and the record also shows exactly that. Some characterizations are also done as a part of this study, which also shows some variations that are there. So with this, I would like to conclude that the synchronous monitoring of current and voltage can provide a very good reliable estimate of the actual arc power and heat input. Most importantly, the recorded metal transfer and melt pool transients provide an estimate of process stability and build dimensions. And if we can analyze this in a fast responsive manner, These can further provide the cooling rate and solidification, also dimensional inconsistency through the layers, and maybe the process can be controlled better the way we do today in normal welding process. And these are some of the observations that we already know are common. The real-time monitoring also shows that yes, they can capture these observations fairly well. The idea remains that if we can now use this kind of methodology to create a feedback control system for controlling the process better. Thank you.